And here we go.
Good grammar and spelling are important, but if you want to write essays that inspire,
During the process of solving an equilibrium problem, for the second condition for equilibrium and the net torque about any point is equal to 0, you have chosen your point, perhaps here, and you're trying to determine what forces cause counterclockwise torques and what forces cause clockwise torques so you can gather them on the proper side or assign positives or negatives based on that. Well, you have a writing utensil, use it. If you have chosen your pivot point P to be on this side and you have an up force on this side, then that will be a clockwise torque. And if you have a down force on this side over here, then that will be a counterclockwise torque. If you've chosen, on the other hand, the other side, and you have an up force acting on it, counterclockwise. You have a down force acting on it, clockwise. If you've chosen some point somewhere here in the middle, and you have an up force over here, that would be clockwise. Down force over here, clockwise. Those two would be gathered together. And that's how you do it. Use your writing utensil, move your point P, use your fingers to make a pivot point, and then pivot around that point based on the direction of the forces to determine what is clockwise and what is counterclockwise. Second condition for equilibrium. Net torque about any point in the universe is equal to 0. Any point works.
Okay. Comments, questions? Seems familiar from last time. Okay, so let's go on to our screen. So I just want to give a prelude to what we'll to the example problem that we're problems that we're going to do today. So anyway, let's say that we have a pulley. And it's a radius R here. And then I have a string attached to it. And tension on the string is going to be perpendicular to that radius. And this is my mass M. And then I want to show, once I pull this string downward, that we can see that it's going to be a counterclockwise torque. So maybe I can. So if this string acts by itself, tension goes up this way. I'm gonna call this just tension T. Then obviously the original position of the radius was, say, there. And then once I pull it downward, the radius is going to be turning in a counterclockwise fashion. It's going to be going against the clock this way, rotating around in a unit circle fashion, which is pretty much similar to the video we just saw. We just had a pin, but now I'm just idealizing the radius of this pulley as the pin. And my force downward this way, counterclockwise, if I pull down. Okay. And let's call this mass, for example, 15 kilograms. Arbitrary number. It's going to make sense as we get further along. Any questions on the visual of that? Do we see that if I pull this string down, that the tension of this string here is going to produce a counterclockwise torque about the pulley? Okay. Going on to the next one. If I have a pulley like this, radius r, tension perpendicular to the radius, producing a torque. We're just trying to figure out the direction of it. mg. And then I pull down on this guy. The original position of the radius is there. Then that's going to go in a clockwise fashion. My mass is a little bit lower. And let's call this 20, but it doesn't matter. Just call it anything. I'm just going to pull it downward. Okay. And of course, tension goes back to the source, but you're isolating the system. So this is just one tension here that's going to be pulling on the right side. It's going to, if left alone as it is, this right here is going to produce a clockwise torque. The torque is going to be about the center of the circle. All of the angular quantities are with respect to the axis of rotation: torque, angular velocity, angular acceleration, angular momentum. Torque is force perpendicular to a radius. And can we see this? Is everybody clear on that? Okay. Okay. Good. And well, now what I want you to do is I want you to get an expression for just write your write your free body equations and your torque equation for each scenario, for each one of these two scenarios. So this is scenario 1, 2. Take a few minutes to do your free bodies and your torque, because we have forces and we have the torque about that axis. Because now, unlike before, the pulley now has mass to be considered. So let's call it mass M. Mass M. So again, find, write force and torque equations for each one, for scenario 1 and 2. We'll talk about it in a few minutes. All right, so let's look at the free body, or the force equations for this and the torque equation. So I'm going to erase this part. And okay, so all the forces in the y direction. Black. So acceleration is going down this way. That's the direction of the whole system is going to be going linearly down. So it's going to be mg minus t equals ma. And then that's only force there. And our torque equation just be tr equals I times alpha. Only one tension over this one radius r. Counterclockwise torque, as we had determined before. So this is going to be a positive net torque. And we can also write it as tr equals I times a over r. Well, how did I do that? We know that the translational, or the linear acceleration here, which is what we've known before in chapter 5 with forces, this a is the tangential acceleration. At equals to r alpha, so alpha is a divided by r. At divided by r is just a. It's just linear acceleration. We could get fancy and get an expression for acceleration from the first equation, substitute it into here, and we can get an expression for tension. We can do all kinds of stuff. Also, this is a solid disk. And if we go back to chapter 10, we can find out the moment of inertia for the solid disk, which is 1/2 mr squared a divided by r. And we can start canceling and all that good stuff. So questions on that? And we can get rid of that. And this goes away. Tension just becomes 1/2 mass times acceleration, which should make sense to you because that is a force. It's 1/2. And we substitute this guy back into the first equation, and we can dance around and get, stuff. Get the acceleration of the system, blah, blah, blah. And then we can go back and get the angular acceleration of the system. At this point, it's playground. The point is all here. Everybody get that? Anybody not get that? If you didn't get it, send me a private note. So go back over it because today we can breathe a little bit. Can do a lot of examples. One second. Okay, we got a question. Another example is coming up. But instead of doing that amorphously, what do you not understand about this example? Because we have to attack it specifically. Because that's really ask a direct question. Well, what does that equation mean there? Something like that. Any question is valid, but I want to get to your specific need. What I will say about this is that in setting this up, there are forces and there's a torque. Old school free body diagram will say, all right, the tension goes up, that's going to be negative. Okay, mg comes down, the acceleration of the system goes downward, so this guy is going to be positive by our convention that all the forces moving with the acceleration are going to be positive, so therefore t is negative. That's why mg minus t equals ma. That's our linear forces. Then our torques, our rotational forces, are going to be the force times the radius, because by definition, torque is force times radius, t times r equals similar to mass times acceleration, but it's the distribution of mass we call moment of inertia about a pivot point, an axis, times the angular acceleration, tr equals I alpha. And then the question was, okay, write the force and torque equations, which we did there. And then we can go crazy and find the expression for tension, back substitute into here if we want. No, nothing's changed. I'm not sure what you're trying to get at, but anyway, we are still doing mg minus t. It's no t equals mg because the system's moving, right? I stands for moment of inertia. So let me just write some terms down. So back to your other question there, we didn't change anything. T would be equal to mg if it was static. You remember, the first picture here was static, and now I'm pulling it, or I'm letting the system move. So therefore, T will just not equal to mg because there's an acceleration in the system, and we have accounted for that here. Okay, so anyways, some terms. And guys, please read your sections. Notes are notes. This is one aspect of your understanding learning. You have to go back. Please do that additional work on your own. It's imperative that you do that, okay? tension. This is just matter or mass that's spread out from an axis point. So back in the day, to your question about I, we just dealt with point masses. That was easy. F equals ma, point mass m, you know, and then we got it moving and all that stuff. Well, now if we have a wheel, then that point mass being in the center, let's say, and all these mass points are going to be spread out from this axis. Depending on where we put our axis, the moment of inertia will change. For an object like this, a disk, you can say it's symmetric about this point. So we don't deal with just m anymore. We deal with a collection of all of the masses that make up the wheel. Each mass I, and we derived using the kinetic energy. Each mass I times Ri squared is what we call the moment of inertia, because now all of these point masses are some distance r away from the center, whereas this was the center, this was everything. Do you see that? Do you understand that? Because we're no longer dealing with points, we're dealing with objects that are a collection of points: wheels, spheres, cylinders, rods, different geometries. Yeah. So moment distribution of mass. Distribution of mass about an axis. And we're going to see soon that this thing called the parallel axis theorem, I can change my axis of rotation anywhere. I can start spinning this wheel from any location. If I do that, then the principal moment of inertia of this particular object, which say mr squared, changes, since I'm on that subject. And then we'll get to the next example and we'll continue the process. But I want to do this. This is back in section 10.5. So parallel axis theorem is like, you can find a new moment of inertia of a system depending on a new axis of rotation. So generally speaking, the easy case is like to spin it about the center of gravity, the center of mass. So that's you're gonna get a particular. So this is a disk. So you're gonna get a particular moment of inertia. So moment of inertia of a disk, 1/2 mr squared. Now, if I spin it about any other point, my moment of inertia changes. All I have to do is get the moment of inertia about the center of mass, which is this, and I add a mass times d squared. So basically what I'm doing is I'm adding the mass of the wheel plus the new distance away from this axis. So whatever this new distance is, squared, multiplied by the mass of the disk, plus the original moment of inertia, gives me my new moment of inertia. That's the parallel axis theorem. Why is it called parallel axis theorem? This was like, imagine that I have these 2 points. This is the center of mass. Moment of inertia about the center of mass right there. And so I do, and I start spinning it about this axis. Imagine that there's 2, I don't know, rods are coming at you from the page. So those axes are parallel to each other. So the parallel axis theorem accounts for this new axis, and therefore the new axis gives you a new moment of inertia I, which is, let's say this will be the disk itself, 1/2 mr squared plus md squared, whatever d is. You can leave it in variables. This will be your new moment of inertia. This will be in meters, that'll be in meters, so it'll, So we'll come back to that as necessary. All I want to do there, I just want to digress because I want to show you that the moment of inertia can shift depending on where you spin the object from or rotate it about, because the moment of inertia is it's relative to whatever point you're spinning. It's not always, you know intuitively that you're not going to always be spinning an object about one point. You can spin it about an infinite number of points, and whatever point you spin it from, your moment of inertia changes by that theorem. So okay, let's do the same thing. Let's go back to our original stuff. Let's get our force equation and our torque equation for this question 2 here, or scenario 2. All right. I think I want to, oops. Nope. Okay. Oops. Okay. So I'll give you a few minutes for that, and we'll keep going. Okay, so we're going to look back at this. The system is moving downward this way, acceleration A. Wanted that red. Okay. Anyway, so yeah, same thing. So the system going down. So we have, you know, pretty much the same thing. Mg minus T, net torque equation, or just torque. It's just going to be T times R. And what would it equal to? Positive or negative I alpha? Oh, let me not forget this. That would be negative. Yes, exactly, Nicole. Absolutely negative. Negative I alpha. Why is mg positive? Because that force is moving with the acceleration. So even though it's on the other side, it still moves with A. And also, I'm not. This is separate. I'm not considering this at the same time. That's the next example. So if it's moving down this way, it's accelerating down. Mg points down. Mg is positive. Acceleration, pretty much. I mean, in any case, going back to the regular forces, the convention, you can set up your own convention, but I like to keep it simple, that the direction of linear acceleration, the direction of the acceleration is going to, or any forces that moves with that acceleration are going to be positive forces. So tension goes the other way, that's why it's negative. Yeah. So that's always been established convention. Okay, and then we can rearrange this and say negative I A over R. And same disk and same stuff. So we have a net negative torque because of this clockwise rotation. The other one, it was counterclockwise. Yeah, so at that point, it's semantics. It's just the thing in physics, we always try to establish a reference point, a starting point, some sort of convention or standard and stay consistent with it. If my 0 is origin, okay, fine, everything is going to be with respect to origin. If my 0 is -15, everything is with respect to that. It's all frame of reference. And no matter what you say, if you made that -a, switch everything around, the answer will still be the same. You just change how you look at it. You know, I just like to keep things as positive as possible. Okay. All right. So again, the same thing. I can get an expression for t, which will be -1/2 mr squared, a divided by r. This goes away. There's one of those, and this guy's over here. And so t is going to be -1/2 ma. Keeping in line with the convention, that tension is going to go against the acceleration of the system. So that force is a negative force. Since this is negative, it's going to become positive, and same answers, switched, signs are switched. Okay, next example. So we're gonna do the same thing. Okay, now we're gonna have two parts of the tension. And again, if you recall, we're doing that because both of those strings are, sides of those strings are gonna produce a different torque. One clockwise, one counterclockwise. So in this case, do the same thing. Yeah, write your force and torque equations for this guy. So this is mass M. These are both 15 and 20, so that, linear acceleration down this way. Good. And then also, and then after you do that, I want you to get an expression for T1 and T2. So that's step 1, step 2. All right, keep with red. Or, well, you'll see that it's going to be this stuff. It's still a solid disk. So you want to resolve, you want to get the tension, the torque that each tension provides, and that is, okay, close. It's the other one. It switch around. So T1 will be positive, and T1R is going to provide a counterclockwise torque because it goes back to this scenario here, because T1 is on the left side, and if it pulls alone, it's going to be counterclockwise. So T1 is counterclockwise, T2 clock. because T2 left alone, well, if you blot it out, the system's gonna go clockwise. The pulley is gonna rotate clockwise, and then T1 counter. So T1 is gonna be positive, T1R minus T2R. That makes sense? And since T2, or this mass here, is larger than this, the net torque is clockwise. So the system is going to go down on the right-hand side, and the pulley is going to be spinning clockwise. Hence why our torque will be negative. So negative I times alpha. And again, that's a solid disk, so negative 1/2 mr squared alpha, negative 1/2 mr squared A divided by R. mr squared alpha. That's moment of inertia for the solid disk. And from the rotational kinematics equations, alpha is A divided by R. So Nicole, did you see that? Does that make sense there? Why T1R is positive and T2 is negative. Okay. So make sure that we get these basics. Okay, so tell me what still your question is, because we want to explore this. All right. Are you having trouble seeing the rotation? Because that's a big deal. I've seen this every year because things will rotate. That's why I was in the classroom. I would have two strings and pull one, and you can see the clockwise and counterclockwise. But is the visual the thing kind of resolving the visual? Okay, it's got to internalize what's considered positive and negative is determined by acceleration. I think you're alluding back to the regular force equations, because we're not directly dealing with that with the torques. Because I think let's go back there. If the question was, why is this force positive and this force negative? Am I hearing you right? Okay, why is T1 positive? Because going back here, not quite yet. The reason why T1R is positive is because this string, if you just sub this guy out, like eliminate this string here, left alone, T1R will provide a counterclockwise torque if you pull down. And that's why I was trying to give you the visual before. This is like T1 over here. If you pull this down, if you pull on this string, the pulley is going to spin counterclockwise. And counterclockwise torques are positive. That's why T1R is positive. And conversely, if you just look at T2 by itself and pull that string, the pulley is going to spin clockwise. Much just like this, clockwise spin. But make sure that you're still tracking this mg minus t stuff, like for this example. That part is fine, right? That's old forces. That's nothing new. Yeah. As I figured, you say it's not the rotation, but I think you're still trying to play around with the linear acceleration with torque, I think. Based on your question. So I don't worry about that with torque. All you're concerned with is that, okay, I have a force, I have a radius, I have a torque equation. Force times radius, in this case, the force is tension. Tension times radius equals I alpha. We just have to, it's up to us to figure out, is that I alpha going to be positive or negative? In this case, it's going to clockwise spin, therefore it's a negative torque. Has nothing to do with this, not directly. We've already dealt with this A here. Alpha is in terms of A, we can substitute and all that, but it doesn't directly deal with torque, because all torques produce angular accelerations, hence the alpha. A little bit better? Okay. All right. All right. Tell me, and we'll move on shortly, but tell me, what about this you don't understand? Or is that the issue? You can see why the torque is going to be clockwise or counterclockwise, but the whole acceleration thing. I mean, good. You know this. This is old news. Good. I think the issue is here. Let me know if I'm hitting your question, but based on your question, you're trying to figure out if the A is going to determine the negative or positive torque. Is that it? Yeah. Since we have torque facing up, we're considering what direction the wheel turns, which is in a direction opposing that upwards direction by torque. Let's see if we can simplify all that. Let's go step by step. The other picture, it was static. Okay. This picture here, I'm letting the mass fall to the ground. If I let the mass fall to the ground on this side, the pulley is going to spin clockwise. Torque is force times radius. That's what we got. It's now our job to figure out, based on the rotation, if that torque is positive or negative. Well, it's a clockwise spin, so it's a negative torque. I think it's the rotation visual that's tripping you up. And again, this is a common issue because it's outside. I don't know if my hand can phase in and out. I don't want to do this right hand. let's continue and let's see if something else clicks. And I'll continue to work this out. All right. So there we are. Got our expressions. So now what I want you to do is take this example and do number 44. Let's take about 10 minutes to go back to that. I know we set it up last time. Question 44 out of chapter 10. Well, our basic setup here. I mean, you can just write this down and save a little time. All right. We've dealt with that to a degree. I'm going to erase this part. All right, so we're at chapter 10, page 40, number 44, chapter 10. Yeah. The acceleration is 2.1, and so we'll get to that. Okay, so on number 44, mass 1 here is 20 kilograms, mass 2 is 12.5. So that means that the system's going to rotate in this fashion. It's going to rotate counterclockwise, or the acceleration is going to come up and over like this because this is more massive. Do our free body diagrams. This is mass 1, and T1 is going to go up. It's going to go against the acceleration. And then M1G is pointing with the acceleration, so that's a positive force. T2 is positive, as we see here. And then M2G is negative because it's going against the acceleration. So that's, it helps, we need to know that in order to write our force equations. Negative T1 plus M1G equals M1A. T2 minus M2G equals M2A. And then this was just my, I was just combining all the equations because remember, this is an addition problem. So that's why I did that. Negative T1 plus M1G plus T2 minus M2G equals A M1 plus M2. Is everybody good there on the force equations? Chime in if you don't get that. So that's old school, that's forces. Now, because I had that picture. So this is my torque equation here. All right. So, so T1, okay. So I'm just going to isolate T1. So T1's over here, mass, okay. So I pull down, the system is going to be rotating counterclockwise. Well, anyway, it's going to be rotating that way. That's why T1R is positive, counterclockwise. Just imagine, if you will, if you can, I'm pulling this string down. As I pull this down, this guy is going to spin counterclockwise. Over here, I pull this down. This is going to then spin clockwise. starts to rotate counterclockwise, clockwise. This is why the torque provided by T1 is positive, because counterclockwise by convention is a positive direction. It's unit circle. We start 0, 90, that's all positive angles. Counterclockwise rotations, counterclockwise around the unit circle is positive. T2 clockwise is going to be negative. That's why those angles below the horizontal are negative, negative 45, negative 30, whatever, clockwise. And since the net torque in the system is counterclockwise, the net torque, because this mass is larger, the net, this is going to be positive here. So now what I want you to do is solve for the acceleration of the system. I've given you all of the information. So here's our forces, and here's our torque equation. The answer is 2.1. Let's see if you can get 2.1. And don't worry, Nicole and anybody else, okay? The rotations, we'll work with that, because we want to make sure that we can see that. That's why I was trying to look for some videos that had people just randomly spinning a pulley, so we could actually see that action. I couldn't really find anything. Now notice though, in this equation we have negative T1 plus T2. So even though when we extract this, T1 minus T2 is equal to stuff over here. T1 minus T2, well, we want to get the expression for T2 minus T1, because that's what we have in our forces. So let me just continue with that. T1R, this is the moment of inertia of the disk, times A over R, that's alpha. Got an R left over? Okay, get rid of the R's on both sides. T1 minus T2 equals 1/2 MA. That would be great. We can substitute it back, but we have negative T1 plus T2. So all we do is switch the sign. You know, because that's what we have in our expression. Our job now is to try and get an expression that we can substitute into the forces expression. We're using a torque equation to do that. We're getting an expression from the torque to go back to forces. T2 minus T1. I want to write that. T2 minus T1 is negative 1/2 MA. You see the switch? The reason for the switch is because we had in the original equation T2 minus T1. So we don't have to deal with this because we have 3 unknowns. Now we have an expression for 2 of them. Find the one. Right? It's all going to be in terms of A. So it's going to be negative 1/2 MA plus M1G minus M2G equals A M1 plus M2. Put all the A's together. All of you A's together equals A M1 plus M2 plus 1/2 m. How do we get that? Because this was, remember, m1a plus m2a, and I brought 1/2 over here, 1/2 big M A, and then I factored it out. A factored out, m1 plus m2 plus 1/2 m. Divide, and that's nothing. A will be m1g minus m2g over m1 plus m2 plus 1/2 big M. Put in your numbers, and that'd be 2.1. Set up. I mean, the ultimate goal is to find the time. We use kinematics for that. The first step is get the acceleration. Okay, just factored out, 9.8. Big M1 is 20, M2 15. Mass of the pulley 2.5 or 5. Comes 2.5. Okay. Okay, it said it fell down 4 meters. It is 4 meters above floor, so it falls down 4 meters. So starting from rest, it says resting on the floor. So this is 1/2 AT squared. 2 delta Y over A. And that's how much time it takes to fall down. Dude. 8 divided by 2.1. 3.8. 1.94, 1.95 seconds. Okay. Let's go back. Slow down, you know, whatever. Let's go back. Any questions at where were you lost? Let's make sure it can find you. Or if you follow it, great. So is it still the torque equation that's a little issue? We want to nail this, all right? So formula, yes, for this shape, for the disk is 1/2 mr squared. There's different moments of inertia for different shapes. Spheres are 2/5 mr squared, or maybe some version of mr squared. I think for a circle, it's just mr squared, standard. But, yeah, section 10.5. Oh, so a hoop is mr squared and so on. page 278, table of different moments of inertia. So, all right, so one half mr squared for the disk, and so we cancel the r out here, and then we have one left, and it's both sides, you get 1/2 ma. That would be great if T1 minus T2. If we had T1 minus T2 here, put it in there, but it's switched, so we switch the sign. That's all. T2 minus T1, because we have to conform to the expression and the forces. And so in the torque equation, we switch the signs. Yeah, to conform to what we got. And there's that. Okay. So I'll leave you with this last example. I want you to do this tonight because it's going to be part 1 of your skills test. Now, I'll do my best to make it easy on you, because what I want to do for tomorrow is I want to do I'm going to give you part 1 now, and we'll do part 2 in class. Yeah. So all you're really going to do for the skills test tomorrow, you're going to do the same process for 2 different types of shapes. You're going to have a sphere, and you're going to have a thin spherical shell. Tonight is a sphere. Come back with a solution for the sphere. So let me set that up. Okay. Tonight's homework / precursor skills test. We have a sphere with mass 2m. Sorry, that's m1 and 2m1. I want you to expression for A, acceleration, T1 and T2. All right, one last thing. And give me the expression for alpha. And angular acceleration alpha. Okay, question. Yes, I will. I'll upload it in the next 45 minutes. Absolutely, please do. But I'm going to be your benefactor. I'm going to help you out. I'm going to basically give you all up to the final answer. Yes, my pleasure. All right, so please do this part, because this is going to be part 1. We're going to now attach it tomorrow to a thin spherical shell. And we're going to, the big pulley we don't have to do anything with, but this is part 1. You're going to do part 1 and 2 tomorrow. We'll come back and do both. And then we'll do part 1 in class, and all you have to do is do part 2 for the skills test, and then add them together for the ultimate expression. So part, what the heck? So part 1 skills test. All right, any last questions? Please come at me. I'll be in the office hour at 2:35. Nicole, if you still have a question, please, 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 please come see me. I want you to visualize it. Okay.